Hey guys, this video is about the distance formula. You're going to need a ruler for this video, so if you don't already have one, go ahead and grab one. Alright, the first thing that we're going to do is go ahead and draw a coordinate plane. So you want your x and y axes, and then go ahead and use your ruler to accurately measure 5 little marks on each side. So we're measuring in centimeters. And then you can go ahead and do that for the y-axis as well. I'd like you to go ahead and plot the 3 given points, A, B, and C, up here. So this is just a little refresher from last year, 1, 1, 5, 1, 5, 4. Once you have those 3 points plotted, check in with a neighbor, and you should all have the same points. Our coordinate plane should look something like this now. So I'd like you to use your ruler and go ahead and connect those 3 points to create a triangle. Okay, now it kind of looks like a right triangle, and you would never want to make that assumption unless you have a way to prove that. I'm going to tell you that this definitely is a right angle, but another way that you'd be able to tell is that this is a horizontal line and this is a vertical line, since our x values are the same and here our y values are the same. So we know that a horizontal and a vertical line are always going to make a right angle. So now that we know that this is a right triangle, we can use a theorem that we have learned in a previous video to figure out the side lengths of this right triangle. Okay? So before we do that, we can obviously tell that from 1 to 5 is a distance of 4. So I'm going to label that side of my right triangle as 4, and then from a distance of 1 to 4, right, because our scale is just going up by 1, is a distance of 3. So I've got a right triangle with 2 side lengths, 3 and 4. So if you need to redraw this a little over here, you're welcome to do that. We have 3, 4, and a missing hypotenuse, which, remember, we were calling that side C. So we're going to use a theorem. We're going to use the Pythagorean theorem to solve for our hypotenuse. So I'm going to pause the video and give you guys a few moments to go ahead and refresh your memory on the Pythagorean theorem, solve this together as a group, and then we will hit play and see how you did. If you got that the hypotenuse has a length of 5, congratulations, you did this correctly. You remember the Pythagorean theorem from the beginning of our unit. What I'd like you to do now is go ahead and use the segment addition postulate. Remember, that's the SAP, to find the perimeter of our triangle ABC. So that means we're going to add all 3 segments. We're going to add segment AB plus BC plus AC now that we have it, right? And that's going to give us our perimeter. So that would be 4 plus 3 plus 5 for a perimeter of 12 units. Okay, so this was kind of a lot of steps in order to find the distance of our missing side. Okay, what the distance formula allows us to do is to figure out the length of any distance between 2 points on the coordinate plane. So we're going to flip to a fresh page and now use the distance formula in order to find the length of AC instead of the Pythagorean theorem. And it's going to look very similar because if you notice the steps that we're taking here, we're pretty much just finding the difference in our coordinates, right? 5 minus 1 is how we got the 4. And then for our vertical length here, 4 minus 1 is how we got the 3. So if we can do that by making a right triangle, if we can do it without making a right triangle, it's going to be a lot quicker. Okay? So our distance formula is the difference in the x's. So I'm going to do x2 minus x1 squared, just like we do in our Pythagorean theorem, plus the difference in our y values, y2 minus y1 squared. And this kind of looks like a squared plus b squared, right? But notice that there's no squared on our distance. Because what do we do at the end of the Pythagorean theorem? I'll flip back real quick. At the end of our Pythagorean theorem, notice how we take the square root of c squared in order to get that side length alone. So wouldn't it be great if we could do that right from the get-go, right? I don't want to know the distance squared, I just want to know the distance. Okay? So now what I would like to do is try to find the distance of that side length AC, right, by just using our distance formula. So we need to know the 2 points. We need to know point A was 1, 1, and point C, which was 5, 4. Okay, so you can label if you would like to x1, y1, x2, y2, because these represent our coordinates. And notice how x2 and y2 are first, and then x1 and y1 are second. It doesn't matter which one you label, number 1, number 2, as long as you are consistent when you plug them in. Alright, so here we go. I'm going to do 5 minus 1, that's x1 squared, plus, following my formula here, y2, which is 4, minus y1, which is 1. And now we are just going to simplify using order of operations. 5 minus 1 is 4. 4 minus 1 is 3, big square root. 4 squared is 16, 3 squared is 9. Add them together, we get square root of 25, which is 5. So we get the same result. And what's nice about the distance formula is, notice, we did not need to go through the trouble of making that big graph. We did not need to create a right triangle. All we needed was the 2 coordinates, and we plugged them right in and got the answer that we wanted. Let's try this with a few more examples. Example 1. Find the distance of segment DE if the point D is at 1, 3, and the point E is at -2, 4. So this example has a negative value. We want to watch how that affects the problem. So step 1 is we're going to label our points if you feel that you need to do that. So I'm going to do x1, y1, x2, y2. And then we're going to set up our distance formula. So I always want to label what I'm finding the distance of. Don't forget that big square root. And we're just setting it up. So the first thing that's going in my parentheses is x2, which I labeled as -2, minus x1, which is 1, y2, which I labeled as 4, minus y1, which is 3. Okay, now we simplify. -2 minus 1. Think of it this way. If I owe you $2, and then I owe you another $1, now I owe you $3. Don't get mixed up with those negatives. That's the number one thing people mess up in this chapter. 4 minus 3 is 1. -3 squared. That's -3 times -3. Negative times a negative is a positive, so this is just 9. 1 squared is 1. Add them together, we get the square root of 10. Can the square root of 10 be simplified? No. No perfect square goes into 10. It's not a factor. So we are done. Okay? And example 2. We'll try one more. Find the distance of EF if we'll use the same coordinates for E, -2, 4, and F is at 0, -4. So now we have two negatives. So we're going to set up our problem. And then we can plug in. So I would suggest, at least until you're comfortable, to start labeling. And it doesn't matter if I label this 1 or if I label this 1. So let's do this. x1, y1, x2, y2. As long as you're labeling them both the same, it doesn't matter if they're both 1 or if they're both 2. Here we go. -2 minus 0. y2 is 4 minus -4. Again, -2, well, minus 0 is just going to be -2. 4 minus -4 minus a negative, that's really a plus. So that's going to give us 8. Same situation we had in example 1. When you have a negative value in parentheses and you're squaring it, it really is just positive. So this is -2 times -2, 4. And 8 squared is 64. Add them together to get the square root of 68. Now we want to test that to see if any perfect square goes into 68. I noticed that it ends in an 8, which is likely that a 4 goes into it. So I'm going to test that. 68 divided by 4, see if that works. And it comes out to be 4 times 17 is the same as 68. So square root of 4 is 2. 17 is a prime number, which means that it cannot be simplified. So segment EF has a length of 2 root 17. So just like we've been doing for the last few sections, when you get a square root, you want to always test it to see if it can be simplified. And you do not want to get a decimal. You should be able to do these problems without a calculator because we're not typing in square roots. Okay?